G'day viewers. In this segment I'm going to talk about rate and delay guarantees for quality of service in the future internet. So we've talked about differentiated services, which provides different kinds of treatment, preferential treatment for different kinds of traffic flows. But in this segment we want to go beyond that and talk about how you would guarantee performance for different traffic flows across the network. This is to provide a kind of hard quality of service where you get firm guarantees for your kind of traffic regardless of what everyone else is doing. And it's something that might be used in the future internet one day. For a little bit of motivation, just consider what we've talked about so far. We've gone through Skype scenarios and BitTorrent and so forth. But sometimes what you would really like is a guaranteed service. And this is a service that's more like the telephone network. In the telephone network, when you put bits in, it's as though they go through a pipe, they come out with a well-known rate and a well-known delay. In fact, you get this minimum rate, well actually you get a fixed rate with the telephone service, and a maximum delay, again it's fixed with the telephone service, regardless of what everyone else is doing with the network. Why might you want such a strong service? Well, you might want it for different kinds of hard real-time users. For instance, consider here that you've got a robot at the other end or something you're controlling. It's not going to be too good if control traffic to or from this robot, can't get through just because someone else is playing their video, or does get through and it arrives a few seconds too late when you were meant to turn the corner a while ago. If you're really going to be able to operate that and other services over the internet, as well as classic services like voice over IP under very stringent delays, then you would like to have a network that can deliver these strong guarantees. Now, the question really is just, how can we do this? I mean, actually, can we do this effectively? You could certainly build your own network. You could provision a dedicated service, almost set up a different wire or a different network for this traffic where you wanted the guarantee. That would give it a certain rate, and if you fix the path, you get a certain delay, and especially if no one else could use it. But that would be expensive. The whole point of networking the way we do it with the internet, and we use statistical multiplexing and packet switching, is to share the bandwidth. That makes networks much more cost effective. So the real question here is, can we have a statistical multiplexing style network where we use packet switching, but at the same time get some hard guarantees? So we could make it look to this device here like it really had its own guaranteed network. Well, the answer is yes, and I'm going to show you how to do that. At least I'm going to sketch this kind of quality of service in the coming slides. So I'll just go through the various components. Before we look at rate and delay though, there's one point I need to make. That's about admission control. So the setup here is that we have a flow F, and we want to be able to guarantee a rate. It should be at least R megabits per second. It might be more than R if no one else is using the network and we can get more traffic through, but no matter what happens, we want at least R. Similarly, the delay should be at most D seconds. It might be less than that because no one else might be using the network, so we might get our traffic through with a minimum of queuing. But even if everyone else is going crazy, our delay should not exceed D seconds. Now, to do that, we've got to decide, if someone comes along and says, hey, I have this flow and I want this rate and this delay, we need to decide whether we can admit that flow to the network or not, and whether we have to reject it. This is what's called admission control. It's really like using the telephone network. When you make a call, if you're able to get a dial tone through to the other side and someone picks up, the network has accepted your call, and it should be sending traffic through with a fixed delay and making sure you get the bandwidth you need, at least in the classic telephone network, before it was all implemented with voice over IP. Now, on the other hand, it's possible sometimes that you might try and ring through. If you've ever tried to ring through on Mother's Day internationally in the old days, you just might not be able to get a dial tone on the other side. The network would be blocking your call. There's not enough capacity for it to admit your call and make sure it can give everyone the bandwidth that it's promised. So it would reject your call or block it. This should happen infrequently, or you don't have a very well designed network and you're not going to have very many customers. But it could happen. The key point here is that to be able to make guarantees at all, we need admission control, because we need some way to control the load in the network. Otherwise, we could get overloaded and not be able to meet our guarantees. So assume we have admission control. Now I want to move on to rate and delay guarantees. How are we going to do it? First of all, rate. And we're going to consider a delay at a rate guarantee, at a router, one router. And then we'll move along the network path. So here's our router. It's down here. It's in our usual box. Now we have a flow here, flow F, that I want to concentrate on. The router has a weighted fair queuing scheduler. You're just going to need a scheduler that's more complicated and more powerful than a FIFO scheduler to be able to provide any guarantees. We have, going out here, a link that has 100 megabits per second of bandwidth, it says there. So I would like to know what kind of rate guarantee we can give flow F through this one router. What do you think? Well, there's weighted fair queuing. There's some number of other flows. We're not quite sure yet. We can see that this flow has a weight of 10 and the other flows have different weights. Well, what could we do? Actually, I need to tell you a little more before we can really work out a rate. So let's consider, first of all, the case where we simplify weighted fair queuing and we just have n different flows here, including flow F that we care about, and each of these flows has weight 1. Okay, well in this scenario, if you remember your weighted fair queuing, you would expect that each of the flows is going to get an nth share of the bandwidth under load. That means if all of these queues are full, each flow is going to get 1 out of n packets, 1 out of n times it's going to get to send its packet. If the other queues aren't full for some reason, someone's not using their share, everyone else will get more, but you'll get to send at least 1 out of every n packets, if all packets are the same and everyone has weight 1. So if you like, we could divide the 100 megabits per second into n shares and everyone's going to get 1 of those. That's the case where there are n flows with weight 1. So now let's see if we can do our weighted fair queuing example. Suppose now our flow F that we're interested in, it has weight 10. And we don't know how many other flows there are here. Actually, it turns out it doesn't matter. But we do know the sum of the weights of all flows is 100, I say here. So here are all of the other flows. Actually, I mean all flows, including flow F. If we sum up all of their weights, that's equal to 100. That's what we know. Well, if flow F has a weight of 10 and the total weight is 100, actually flow F is going to get 10 on 100th parts out of every 100 packets, say, they get to be sent. Flow F would get to send 10 of them times 100 megabits per second. That's 10 megabits per second. So flow F would be guaranteed a rate of 10 megabits per second in this scenario. Let me just clean it up here. Here it is. So if you think about that, you might have to go back and review your notes about fair queuing. But given that the weight of this flow F is 10 and the total weight is 100, what it means is that we're going to get 10 out of 100 shares of the output bandwidth in terms of bits. And 10 out of 100 shares, or 10% of this output link, is 10 megabits per second. So yay, we have a guarantee. Let's see if we can get a network guarantee now. Because I don't want to guarantee a single router. I want to guarantee across the whole network path. You can see the whole network path goes through here. And so far, we've just done this one router here that's shaded in pink. However, you should realize, if you think about it a bit, that if we make the same condition at every particular router, I mean, if I have a guarantee of 10 megabits per second at the first router here, and 10 megabits per second here, and 10 megabits per second here, I will get 10 megabits per second along the whole path. So what we want to do is, for every router, set the weights to make sure you get 10 megabits per second, say. So I've written this a little more generally here. The condition for every router to get R megabits per second is just that you set the weight appropriately. So you need to make sure that the fraction of the weight, fraction of the total weight, that is the weight that we give to the flow F, divided by the total weight at that router. I here is the number of different routers, so this has got to hold at every router, times the output link should be at least should be equal to R, and that will give us equal or more to R, and that will give us at least R megabits per second, no matter what the traffic patterns are. So you can see here you could have 10% of a 100 megabit per second output link and you get at least 10 megabits per second. Or you could have 20% of a 50 megabit per second output link. And you get 10 megabits per second. And if you got this at every router, you will get it along the path. Okay, so now we know how to get a rate guarantee. What about a delay guarantee? This is actually the trickier case, so let's move on to this. And really, we want to know about the queuing delay. The delay we're going to get is going to be at least the propagation delay and the transmission delay to packetize things, to send individual packets as they're stored and forwarded at every router. That's a minimum. You're just not going to beat that because the signal has to propagate. Our question is how much larger than this latency is the delay going to be because of queuing? Given that we already have this situation where we've made a rate guarantee. It'd be wonderful if we made a rate guarantee and that meant if we'd set all of the weights correctly and we were getting at least our R megabits per second, that meant that we incurred no queuing, say. Well, that's not the case. If you think about it, you should realize that the queuing delay you're going to get at a router depends upon the characteristics of the traffic flow. Now, I might be getting R megabits per second through the router, but if my traffic, the instantaneous rate is going to go up and down, just depending on the statistics. If this is a robot, it might be generating traffic at different rates depending whether things are being moved or not. Well, if the rate exceeds R megabits per second over short intervals, whenever it exceeds that, the queue inside the router may well grow. If other people are using their shares and we're only getting our minimum, the queue will grow. If the queue grows, the delay will grow. So the queue built and the delay is going to grow. So the insight here is that if you want any delay guarantee, which you can state conclusively, then you need to shape the traffic to enable a guarantee. To do that, we need to constrain the burstness. And I think you know how we're going to do that. It says so there, we're going to use token buckets. Great. We knew they were useful for something. So here's our token bucket picture. So what we're going to do is assume that the traffic flow F is shaped according to an RB token bucket. What that means, if you recall your RB token bucket, is that we will get a long-term rate of R megabits per second, and we are, in addition to that, allowed to send a short-term burst of up to B bits, as long as we don't exceed that rate over time. So if we send a burst, we're going to have to slow down after a while to recover. So now let's think at one individual router, what kind of delay guarantee do we have if we change our traffic so that it is now shaped by an RB token bucket? So if you like, what's coming in here is an RB token bucket. And we have the same setup inside the router. We have the different flows and we have a weight here. It happens to be 10 here, and we have 100 megabits per second output link here. So we just need to work out what delay we're going to get out. What do you think? It's actually difficult to think about what delay we'll get out. It really depends on the details of exactly what packets are sent when by the source. Now, what we can say though is that the worst case for delay is going to be if someone sends a burst and the traffic arrives all at once. They just go blat, and a burst of B packets arrives all at once. If they were spread out more over time, they're going to cause less of a queue to build up, and it's going to be not so bad in terms of delay. So the worst case is sending as fast as you can traffic all at once. That's this burst B. Well, if that arrives at the router, it's going to fill up the queue. Say it arrives instantaneously, the input link is really fast, and we might fill it up to here. That last packet, that's going to experience a queuing delay of up to B on R seconds. So the burst size divided by the drain rate, it's going to take that long for this packet to go through the queue and get out of there on the link on the other side. So that's the worst case delay that can be experienced. Since we just blew our burst all at once, we can't make this queue any bigger. It can only fall over time. So no one else is going to get a bigger delay. So B on R is the worst case through a single router. What about the delay across all routers on a path? Because again, I care about the delay not just for this router, but for all of these routers. And you can see I've shaded them all in pink because I care about the delay across the entire path. Well, actually, this is kind of tricky to work out. This is, difficult for us to do in detail. And the reason for this is that all of these routers, so as I go through one, I might get a delay, another one, I might get another delay, and it's going to add. So unlike the rate case where they just all had to be large enough and we really cared about the minimum you get along the path, here for delay it's additive. So all of the routers are going to add their delay. Now we could just say, okay, one router, it can't be any worse than B on R. So for the whole path, if you've got n routers, it's n times B on R. But that can be quite a large number. So this can be a very loose balance. It's not really very useful in practice for coming up with a good guarantee. So I'm going to give you an intuitive argument in the following slides about the delay band we'll get, which is going to be much better. It's actually a kind of cool argument too. So observe that if the traffic is perfectly smooth at rate R, there's no burst coming in, then you don't get queuing delay at any of the routers. So if the traffic is perfectly smooth, we send one packet in here, there's no queue, and so it goes out immediately into the next router, and then the next router, and the next router. Here, from the source, we send another packet, but we don't send it immediately, we wait so that we're pacing out the packets at rate R. That means that by the time the second packet comes in here, the first packet is cleared out of the queue. So the second packet goes right to the beginning and it's ready to be forwarded again. And so on at the next router and the next router. So we're in good shape here. We're getting no queuing delay. So no queuing. The only latency that we'll end up with is the old propagation and transmission delays to send packets along this path and through all of these store and forward routers. But no queuing. That's great. Well, that was the best case. What about the worst case? What about if we don't smooth traffic, but we send a burst? Let's send that horrible burst. So the burst goes right in here into the first router. All of these packets come in at once. Rats, that's pretty tricky. So we said that you can pay a queuing delay of up to B on R going through this router. Now, here's an interesting observation. Suppose we do that. Well, the traffic might go into the router as one big burst, but it's going to come out smoothly. If smoothly, in the worst case, it will come out one packet appropriately so that it's been sent out at rate R. Why? Well, because we guaranteed that rate. It could come out a little faster, but in that case we won't get the whole queuing delay of B on R. It'll come out nice and smoothly at rate R if everyone else was using their bandwidth and we were just getting our R megabits per second. So if it comes out at rate R, then guess what? It's not going to queue at the next router. No queuing. So it will then go on to the next router where there's no queuing and so forth. So the interesting observation here is that because as you pay for the burst it's smoothed out, you only pay for the burst delay once. It might not be this router I've chosen here. You might end up paying for some reason in the middle router or the end router. Or you might pay half across two routers, but you don't pay for the burst more than once as it's delayed and smoothed. So interestingly here we end up with this situation. The delay, that is the queuing delay across all of the routers is B on R, the same at a single router. And of course our delay then has these various latency terms to set along the path, plus the B on R queuing. Pretty cool, huh? Okay, so just to recap, we've now come up with a strong quality of service result, which if you were designing a network could let you provide hard rate and delay guarantees. To do that, we needed all of these pieces. We needed a network with traffic which was shaped according to RB token buckets, and we needed routers which implemented weighted fair queuing scheduling rather than first in, first out. And we had to adjust the weights, and from all of those weights we could compute the rate and the maximum delay we'll get across the network. So we got those delays even though we have a network with statistical sharing, so all other traffic sources can take advantage of whatever packet, whatever bandwidth is available just by packet switching. So when we do all of this, we end up with these guarantees and the guarantee is for the minimum rate. You might get more if someone else isn't using the network. And the maximum delay. You might get a better delay if there's less traffic that's in the way. And it's important to realize when I say guarantee, I really mean a guarantee here regardless of what the other flows are doing on the network. Doesn't matter if they're crazy or not, you still get to meet your guarantees. So that is how we can provide strong quality of service in a network.